Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. Today's talk is by Professor Aritra Mitra, and he will be speaking on collaborative decision making under adversarial and information constraints. Professor Aritra is currently an assistant professor at the Department of Electrical and Computer Engineering at North Carolina State University. His research interests include control theory, optimization, statistical signal processing, and machine learning, and distributed algorithms. Previously, he was a postdoctoral researcher at the University of Pennsylvania from 2020 to 2022. Prior to that, he received his PhD degree from Purdue University in 2020, his MTech degree from IIT Kanpur in 2015, and his BE degree from Jadavpur University in 2013, all in electrical engineering. He was a recipient of University Gold Medal at the Jadavpur University and the Academic Excellence Award at IIT Kanpur. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. We will be pasting in the links in the chat box. Please do check. Finally, we request the online audience to keep your microphones on silent for the duration of the talk, except for asking questions. And for questions, you may raise your hand, unmute yourself, and ask directly, or type them in the chat box so that we will relay your questions. Over to you, Professor.
Thank you so much for that kind introduction, and thank you to all the organizers of this wonderful seminar series for this invitation. It's really my pleasure and honor to be speaking in front of this audience. What I plan to do today is talk about some problems that I've been thinking about over the last year or so, broadly centered around the theme of sequential decision making under multiple forms of uncertainty. When we usually think about sequential decision making problems under uncertainty, or what's known as reinforcement learning, we associate the uncertainty with some lack of knowledge about the environment that a learner or an agent is interacting with. And this uncertainty is usually modeled by making some nice structured stochastic assumptions. In this talk, what we want to understand is what if there are additional forms of uncertainty that are less structured and in fact can be completely adversarial? How do we perform decision making under these multiple forms of uncertainty? Okay, so with that in mind, let's get started. Since this will be a talk that's centered around reinforcement learning, let's start by acquainting ourselves with what a standard reinforcement learning setup looks like. So what I'm showing over here is an agent that's interacting with an unknown world. To know this world better, what the agent does is that it pokes the world by taking some actions. The world then responds by providing some feedback in the form of rewards. Looking at these rewards, the agent gains a better understanding about the world that it's interacting with. And this in turn allows the agent to take better actions over time. And when we use the word better, we need to specify some kind of a performance measure. So the typical performance measure that one cares about in these problems is to maximize some kind of long-term cumulative return. So in the end, our goal is to come up with a good sequence of actions, or what's known as a policy, to maximize long-term cumulative returns subject to some initial uncertainty in the environment. And it's really this uncertainty in this environment that makes this a learning problem. So that's the standard reinforcement learning pipeline in a nutshell. And reinforcement learning in general has found a lot of success when it comes to a variety of applications, ranging from robotics to games, etc. But when we think about these contemporary applications, we need to often contend with high-dimensional information, high-dimensional data, and the state and action spaces in these problems can be really large. As such, the reinforcement learning algorithms that we often end up deploying in practice end up being really data hungry, meaning that if we care about a certain performance level, we need to eat up a lot of samples to achieve such a performance guarantee. So a natural question that arises here is, how can we hope to reduce the sample complexity of learning for complex reinforcement learning tasks? So a natural idea here is to envision a scenario where instead of having just one agent interact with the unknown world, let's suppose we have multiple agents interacting with this world, and let's allow these agents to exchange information among themselves. Now, at this point, intuition should dictate that because each of these agents are interacting with the same world by exchanging information, they should be able to reduce the uncertainty associated with this world much faster than if they acted alone. And this in turn should lead to some collaborative performance gains and allow each agent to do better than what it would if it acted individually. Okay, so all of this is quite intuitive. But the implicit assumption that we make here is the fact that each of these agents are acting in a truthful manner. They're acting reliably, exactly as expected. But when we think about really large-scale settings, we must account for the possibility of outliers. We must account for the possibility of agents that deviate from nominal behavior and act in unexpected manner. In particular, we need to account for the possibility of adversarial agents. So this leads to an interesting tension. On the one hand, collaboration gives us hope that we should be able to reduce the sample complexity of learning. But on the other hand, if you're not careful about how we are aggregating information, we might end up learning nothing at all because of this adversarial contamination. So the question before us is that if I'm an agent over here, do I just choose to ignore all this side information, or do I willfully accept the side information, knowing fully well that a part of this information can be adversarially contaminated? So in short, does more data help us or does it hurt us? And the question that we want to understand in the first half of the talk is, how do we take good decisions under both environmental uncertainty and adversarial feedback? So in this setting, the adversarial feedback is what constitutes the additional form of uncertainty. In the second part of the talk, we'll turn our attention to yet another form of uncertainty, namely uncertainty injected by information or communication constraints. The motivation here stems from the fact that if you think about large-scale learning paradigms, such as federated learning, you usually have several thousands of devices that exchange high-dimensional model vectors or parameter vectors over low bandwidth channels. And this constitutes this creates a huge communication bottleneck. And the need arises to limit the amount of information that's being exchanged without compromising too much on performance. So our main goal here is to quantify the effect of communication constraints on the finite time performance of reinforcement learning algorithms. And what makes this challenging is precisely this finite time aspect of the problem. Okay, so in the second part of the talk, I'll spend some time talking about our initial results on this talk. So this brings me to the outline of the talk. I've been alluding to two key themes. One is adversarial robustness, the other is communication constraints. Each of these themes have been extensively studied for static optimization problems, supervised learning problems. But when it comes to sequential decision making, there's much less that we know about these challenges. So in this talk, what we want to do is limit our attention to perhaps the simplest class of reinforcement learning problems known as bandits. And in particular, we'll think about the linear stochastic bandit formulation. So I'll assume no prior background on bandits, and I'll provide you with all the technical background that's needed to understand the results of this work. Once we set up the background, then I'm going to jump into the first part of the talk that involves collaborative linear bandits in the presence of adversarial agents. I'll walk you through the main results. I'll also spend some time talking about our algorithm and provide a proof sketch. And in the second part of the talk, we'll introduce a new linear bandit formulation subject to a bit constrained channel model. And again, I'll walk you through the main results. And this talk is based on two pieces of work. So it's based on two papers. For the first part, the work is based on a paper that showed up at NeurIPS last year. And this was work with my postdoc supervisors at Penn, Hamid Hassani and George Papas, and the student Arman Adibi, who I was mentoring at the time. And the second part of the talk is based on a paper that showed up earlier this year at the Learning for Dynamics and Control Conference, or the L4DC conference. And this is also work with my postdoc advisors, George and Ham. So with that, let me start by providing you the background that you need on bandits. And let me just point out that if you have questions at any point, please don't hesitate to stop me and ask me your questions. So an example usually helps, and I thought I'd start with something that is hopefully relatable. Before I came to Raleigh, I spent a couple of years in Philadelphia. And the first thing that I did when I arrived in Philly is to ask myself, what's the best Chinese restaurant in the city? I'm a huge fan of Chinese food, so this is a very natural question for me to think about. So here are some options or candidates for the best Chinese restaurant. Let's think of each of these candidates as an action or an arm that we can sample or pull. Now, each time we visit a restaurant or sample an action, we are going to get some noisy feedback about the quality of that restaurant. And for the sake of argument, let's suppose that there is a clear winner here. There is indeed a best restaurant, and let's suppose that that restaurant is Dim Sum House. Okay. Now, to make the setting interesting, what we're going to say is that each time we pick a suboptimal action or visit a restaurant that's not Dim Sum House, we pay a price, and that price is, let's say, 1 unit. It doesn't matter if this is 1 or some bounded constant. Now, let's suppose the total number of visits that we make is T. T is also what's known as the horizon of the problem. So then our goal here is to play a sequence of actions such that the sum of prices that we accrue over this horizon T divided by T, that goes to 0 as T goes to infinity. So what's the intuition here? If we interpret picking a suboptimal action as a mistake, what we are really looking at in the numerator here is the sum of mistakes that we make over the horizon T. And we really want the average number of mistakes to disappear as time goes to infinity. That's a notion of learning. And it's really the noisy feedback in this problem that makes it a learning problem. And it's what creates what's known as the exploration-exploitation dilemma. Namely, do we play the action that appears to be the best right now based on all the historical information that we have received so far? Or do we play actions that we haven't really explored too much? And you can perhaps already see that neither naive exploration nor naive exploitation are good strategies. What would a naive exploitation strategy look like? You arrive at the city, you go to the first restaurant, you happen to like it, and you keep going there. But this is not a good idea because this precludes the possibility of discovering better options. On the other end of the spectrum, what would a naive exploration strategy look like? You wake up each day, you have 3 restaurants, so you roll a 3-face dice, and whichever face comes up, you go to the corresponding restaurant. But this is also not a good strategy because if you play this strategy, then on an average, you'll be spending 2/3 of your time exploring the suboptimal actions, and hence this ratio will be 2/3 on an average. It won't vanish as T goes to infinity. And what's bad about the strategy is that you're not using any feedback. You're not using any historical information to guide your decision making. You're leaving things to chance. So long story short, neither naive exploration nor naive exploration are good strategies. We need to strike a balance between them. And this is precisely what's at the heart of reinforcement learning problems. So hopefully that gave you some intuition about the basic multi-arm bandit problem. What we'll look at in this talk is a generalization of the basic multi-arm bandit problem known as the linear stochastic bandit problem. And the idea here is that in reality, you might encounter scenarios where the action set is really large. So it might be infeasible to go and sample each of the actions several times. So really what we're hoping for is that by sampling some actions, they reveal side information about the other actions. So we're really hoping for correlations between the actions. And the linear bandit model is one of the simplest models that capture such correlations. So what's the linear bandit model? We have an action set, a finite action set that comprises of k actions. Each of these actions reside in some compact set within Rd. And at each time step t, a learner is going to pick an action denoted by a sub t from this action set. And upon playing this action, the learner is going to receive a feedback or a reward denoted by yt. What is yt? Yt is the sum of 2 terms. The first term is the inner product between the action that got played at time t and some latent parameter theta star that captures correlations between the actions. So you can interpret theta star inner product at as the true mean reward that you get by playing action at. Yeah, but what the learner gets to observe is not this true mean reward. Instead, some additively perturbed version of this true mean reward, where the additive perturbation is some very benign noise. It's just zero mean Gaussian noise. Then we'll assume that the noise sequence is IID. So given this observation model, our goal is to minimize what's known as the expected cumulative regret. Let me explain what this object is. But to do that, I need to first tell you what the best action is. So the best action is the action within this action set that is most aligned with the latent parameter theta star. So why do we call it the best action? Because it's the action that leads to the highest inner product and hence the highest mean reward. So now if you look inside this summation here, you will notice that there are two terms. The first term is the highest expected reward that you can hope to get at any round, because this is the inner product between theta star and the best action. And what we're subtracting off from this term is the mean reward that we actually get by playing the action that we actually play at time t, which is 80. So you can think of this difference as the instantaneous regret suffered by the learner for not knowing the best action ahead of time. And if we sum up these instantaneous regrets over the time horizon capital T, and then take the expected value of that object, we get what's known as the expected cumulative regret. And our goal here is to play a sequence of actions so that this regret R sub T grows sublinearly in the horizon T, or in other words, RT divided by T goes to 0 as T goes to infinity. Okay, so that's the standard linear bandit formulation. And this is really all the background that we need for this talk. So with
just
that,
one question, Aritra,
yes,
this is Vaibhav here. So
yeah.
This is called a linear because it's the measurement is a linear function of the action. Is that why the word linear is?
It's linear in the parameter, unknown parameter theta star. So you can think of this as a linear, a linear observation model where the unknown object is the parameter theta star.
Okay, but it's also linear in action, right? So
that's correct. That's correct. So the linear, in this case, the reason why we call it linear is because it's linear in the parameter theta star.
Okay. And why do you call it as a correlation parameter? What is the
because look at, if you see that if you play two different actions, let's say you played two different actions A1 and A2, the rewards that you get to see both come through this parameter theta star. So even by playing two different actions, what you get to observe, the object that you get to observe, it has some correlations between the actions that's captured via this parameter theta star. Because both
it's like an underlying hidden parameter that relates different rewards, right?
Exactly.
By different actions. Okay.
Exactly.
Okay, thanks.
So with that, let's jump into the first part of the talk, which is going to be on this setting involving collaborative bandits with some adversarial agents. Okay, so what's the setting here? We have M agents, all of whom interact with the same environment, the same world. And we're going to allow these agents to exchange information via some central server. Now, if you think about the observation model for each agent I, it's the same linear observation model that I showed you a couple of slides earlier. And in particular, YIT here is the reward obtained by agent I at time t, which is the inner product between this unknown parameter theta star and the action taken by agent I at time t, denoted by AIT. And again, you have this additive zero mean Gaussian noise. And we're going to assume that the noise is independent across the agents. Now, there are two things to take note of here. The first thing is that it's the same underlying parameter theta star that governs the observation models of each of the agents. And secondly, the action set is the same for all the agents. Okay, so all agents are sampling actions from the same actions. So given this, you'd expect that by exchanging information, each of these agents should be able to reduce the uncertainty associated with each action much faster than if they acted alone. So essentially, you should be able to reduce the variance associated with this noisy observation model. That's the intuition. And this should again help, it should lead to some collaborative performance gains. But what makes this setting interesting is the fact that we'll allow a small fraction of the agents to be adversarial, and we're going to allow them to act in an arbitrary manner. So then the question that we want to understand is, can collaboration still help us? And if so, what are the fundamental limits of collaborative performance gains that we can hope to achieve in this setting? And as an example to keep at the back of our mind, let's think about these agents as people who are exploring restaurants in a common city. And each time a person explores a restaurant, it writes reviews about that restaurant to some web recommendation server. And you can think of these adversarial agents as people who write spam reviews. So these are capturing spam reviews, the adversarial agents. And the question is that if I'm an agent over here, do I benefit by looking at the reviews written by other people? In terms of performance measure, we are going to be thinking about the same cumulative regret metric that I'd shown you a couple of slides earlier. And we are going to be thinking about this cumulative regret for each good agent type. I've dropped the expectation here. So this is a random object. And what we'll do is provide high probability bounds on this random object, which in turn will lead to bounds in expectation. Now, what's a natural strategy that an agent can adopt here? Well, it can just choose not to talk to anyone, right? So it can just explore and exploit on its own. And if it does something reasonable, then the best regret that it can hope to achieve without talking to anyone else is order square root dt, where d is the dimension of this latent parameter and t is the horizon. And you can notice that if you divide this by t, then the ratio does in fact go to 0. So in other words, each agent will be able to achieve sublinear regret even on its own without talking to anyone else. But the question is, can we do better? And can we do better in the presence of adversaries? So this is really the tension that I'd alluded to at the beginning of the talk. On the one hand, collaboration gives us hope that we can perhaps improve upon this regret bound, the single agent regret bound. But on the other hand, if we are not careful about how we are aggregating information, we might not end up making any improvement at all. In fact, we might not end up learning anything at all. Okay, so does more data help us or hurt us in this context? And the reason why this is an interesting question is the following. Let's suppose that you're right at the beginning of the learning process. And consider any good agent at this process, at this time step. Now, since you're really at the beginning of the learning process, each action has been sampled very few times. And this includes the best action. So at this point, there is really large statistical variability around the quality of the best action. And hence, the best action may not appear to be the best right at the beginning. It might appear to be a suboptimal action. Now imagine that a bad agent reinforces our belief at this point that the best action is indeed not so good. If we are not careful, we might end up eliminating the best action really early into the learning process, in which case we might end up suffering linearly. This is the point here is that we need to somehow disentangle the statistical variability in this problem from the uncertainty injected by the attackers. So given this context, our first contribution here is to propose a new bandit algorithm called RCLB, which is a phased elimination algorithm. It relies on distributing the task of exploration across the agents. And really the key ingredient is the construction of certain robust confidence intervals. And I'll talk about this algorithm in detail in a couple of slides. In terms of the performance guarantee that we can hope from this algorithm, here's our main result. Let's suppose that the corruption fraction is less than a half, because if more than half of the agents are adversarial, then there's really no hope of learning anything meaningful. So suppose alpha is less than half, then given any failure probability delta, which lies between 0 and 1, what we can prove is that with probability at least 1 minus delta, we can establish the following regret bound on the regret of each good agent type. Okay, so let's unpack the regret bound on the right. If we ignore this alpha term for a moment, notice that this square root dt is the single agent regret. What we achieve over here is the single agent regret scaled down by the number of agents, m. So square root m is the scaling factor here. And this is really what captures the benefit of collaboration. But at the same time, because we are participating in a system that involves adversarial agents, we are paying a price. And the price is this additive effect of the adversaries. You have this corruption fraction that shows up over here in the bound. So the main takeaway is that if the corruption fraction alpha is small, and in particular if it goes down with the number of agents m, then there is indeed a clear benefit of collaboration that you enjoy by playing this algorithm despite the presence of these worst case adversarial agents. And if alpha is 0, then this bound is optimal in its dependence on D, T, and M. So really the question is whether this additive alpha term is an artifact of our analysis or whether it's something unavoidable, whether it's to be expected. So that leads to our second main contribution. What we show is that given any policy, you can always construct two different bandit instances such that the regret suffered by the policy will be at least of order alpha square root t on at least one of these two instances. And the key thing to note here is that this is going to be true regardless of the number of agents in your system. So even if you make the number of system agents really large, you can't really get rid of this term alpha square root t. It's going to persist. Okay, so this tells us that this alpha square root t regret term is in fact unavoidable. And combined with our upper bound, this tells us that the regret guarantee that we get is near optimal. Why do I say it's near optimal and not optimal? It's because this lower bound does not have any effect of the dimension d inside it. Okay, if you go back a slide, you will notice that this alpha term gets multiplied by square root dt. What the lower bound is revealing is that alpha square root t is inevitable, but what we have not been able to show thus far is whether alpha square root dt is unavoidable. Okay, so this is a gap in our existing work. Let me pause here to just make sure that these results are clear. Do you have any questions at this point?
Yeah, I have one question. Can you go back to the previous slide?
Yes.
Yeah, so this bound on the regret, is it independent of delta?
It shows up. It's a good question. So there's an O tilde here, which is hiding log factors. So you have a log 1 over delta kind of a term that's showing up inside the bounds, which I'm hiding with this O tilde notation.
Okay, so as you decrease the delta, your bound increases.
That's correct. But it's logarithmic in 1 over delta, so it's not crazy at least.
Okay, thank you.
Good question.
Hi, Aritra. So, what is the proposed algorithm? Are you going to talk about it?
Yeah.
Okay.
I'll talk about it in a couple of slides. Yes.
Okay.
Yes. Okay. So if there are no further questions, let me at least point to some related work on this topic. One natural area that is related to this line of work is this area of robust statistics, where the idea is to compute statistics of data sets like means, variances in the presence of outliers. Excuse me. This is a line of work that was pioneered by Huber and Tukey in the 1960s, and since then there's been a lot of work in this area. I'm just pointing to one representative paper here by Gabo, Lugosi, and Mendelssohn. The other area that is very related to this line of work is outlier robust distributed optimization. I'm using supervised learning and optimizations interchangeably here. There's a lot of work in this space, and I'm only pointing to, again, one representative paper by Peter Bartlett and Kannan Ramchandran's group at Berkeley. But the key point to take note of here is that neither of these problems involve any decision making. Okay, so there is no exploration-exploitation dilemma in either of these problems. And when it comes to collaborative reinforcement learning problems with adversarial agents, there's really not much work. The only two papers that appeared before our work are these works by Abhimanyu Dubey and Alex Pentland, and Daniel Weil, Sanjay Shakota, and R. Shrikant. But each of these papers look at the simpler, unstructured multi-arm bandit problem, and none of these papers come with any lower bounds. So our work can be seen as a generalization of these papers, in the sense that the linear bandit problem generalizes the basic multi-arm bandit problem, and our paper also comes with lower bounds. Okay, so this is the broad space of problems that are related to our work. Okay. So with that, let me now spend some time talking about what the algorithm looks like. And what I'll do first is provide an outline of the main structure of our algorithm, and then I'll fill in the missing technical details. Okay, so our algorithm is a phased elimination algorithm, which evolves in epochs. And in each epoch, the server is going to maintain a set of active arms, which are candidates for being the best arm. And initially, because every arm is equally likely to be the best action, the initial action, the active arm set is going to be the entire action set. Now, what the server is going to do is it's going to ask the agents to explore the arms or actions within this action set. The agents are going to perform some exploration of these actions. And then at the end of the first epoch, these agents are going to construct some model estimates of the latent parameter theta star. Because the notation here is that the subscript denotes the agent index and the superscript denotes the epoch index. Okay, so the agents are going to construct some local model estimates, and they're going to transmit these estimates to the server. And at this point, the adversaries can send whatever they want. Now, using these local model estimates, the server is going to do some processing, and it's going to prune the active arm set, and hopefully the size of the set is going to shrink now. And once again, the same process is going to repeat itself. So the server is going to ask the agents to again sample actions within this smaller active arm set. The agents are going to again perform some exploration of the actions within this set. And at the end, you will again have some local models for each of the agents, which are going to be transmitted to the server. The server will further prune the set, and this keeps on happening. So you can, as an analogy, you can think of this as sort of like an interview process where right at the beginning, you have a huge pool of candidates. And the first epoch is really when you're looking at CVs and you're eliminating a lot of candidates really quickly. And then once you're done with that, the candidates that remain are closer to each other in quality. So it's going to take you a longer duration to separate these candidates. And hence the second epoch is longer in duration. Okay, so as we'll see, the length of each epoch is going to double in size. Okay, so that's the high-level structure of our algorithm, but I've of course left out a bunch of details. How do we decide this exploration strategy inside each epoch? How do the agents compute the local models? At the server, what are we doing to compute robust estimates of the means of the arms? How do we construct confidence intervals around these estimates? And what's the idea behind eliminating the arms? How do we do this arm pruning? So let's go over each of these points one by one, starting with the sampling scheme. The idea behind the sampling scheme is that in each epoch L, we only want to retain the arms that are order epsilon L away from the mean of the optimal arm. Okay, and as the epochs progress, we want to be more and more precise in terms of the arms that we are retaining. And hence this precision epsilon L is going down exponentially in the epoch number L. Okay, so in short, as time progresses, we only retain arms that are super close to the best arm. So let's illustrate this pictorially. Let's denote by script AL the active arm set in epoch L. And let's suppose A1 and A2 are two actions within this arm set. So if A1 is the best action, then theta star inner product A1 is the true mean reward corresponding to this action. What we want to do is create this interval of length epsilon L around the mean of this best action. And all actions that have means to the left of this interval over here, we want to get rid of them. Because that's the idea. And it turns out to do that, the number of times you need to sample each action scales as follows. India. The thing to take note of here is that it scales as 1 over epsilon L square. And since epsilon L is going down exponentially in L, you can see that the number of samples is also growing with the epochs. This is why the epoch lengths expand in size. And the other thing to take note of here is that as time progresses, we want to be more confident about what we are doing. So if you want good things to happen in epoch L with probability at least 1 minus delta L, then we want the failure probability delta L to also go down with the epochs. Okay, this is because you want to be more confident as time progresses. So the idea here is that the lengths of the later epochs are going to be longer in size. So if a suboptimal action manages to creep its way into these longer epochs, that's going to lead to a lot of regret. So we want to be confident about such events not happening, and hence delta L is going down with L over here. Now, once these numbers have been calculated, what the server is going to do is that it's going to uniformly distribute the task of exploration among the M agents. Okay, so it's just a very simple uniform distributed exploration strategy. Now, what do the agents do to compute the local models? This is quite simple. So each agent is going to collect all the observations that it receives during epoch L, and it's just going to run a least squares estimate. So this is a linear model, so you can fairly easily compute a least squares estimate over here. Now let's come to the more interesting parts of the algorithm. What does the server do to compute robust estimates of the means of the arms? What I'll do here is first go over a couple of things that I tried out initially and they did not work before I tell you what I do finally, what the final strategy is. Okay, so here's a candidate strategy. Let's suppose that each agent uploads its local model to the server. The server then uses some off-the-shelf high-dimensional robust mean estimator to compute a robust estimate of the latent parameter, theta star. And then for each action within the current active arm set, to compute an estimate of its mean, it just projects this robust estimate of the model onto the action. Okay, so this is a legitimate strategy, but there are two immediate issues with this strategy. If you work out the math here, and this is available in the paper, you will see that the regret bound is off by a factor of square root d, which can be really bad if d is large. And the second issue is that the runtime complexity of these high-dimensional robust estimators can be really large. So in the worst case, they can even be exponential in the dimension. So not only are we thinking about really computationally expensive schemes, the regret bounds are also suboptimal. So this is not a very compelling strategy. Here's another candidate strategy.
Hi, does
Yes.
the server
Yes.
know what is the best arm?
No. So the server doesn't know the best arm. So if the server knew the best arm, it could just relay what the best arm is to each of the agents.
The main idea is that in the screening, keep the arms which are epsilon in the epsilon L distance of the best arm, right?
Exactly.
So
yeah.
how do we execute that?
I'm coming to that. Yeah, in a couple of slides. Yes.
Okay.
Yes. Okay. Yes. So right now what we're doing is we're trying to think about what are the statistics that are needed to do this arm tuning at the server. And one of the basic ingredients that we need is to get some idea about the means of the arms based on the information that's coming from the agents. Okay, so that's the first step. Another candidate strategy is the following, where instead of asking the agents to send up their local models, the server is going to ask each agent to send up all their raw observations, all the rewards that they observe during the epoch L. Now, using these observations, what the server can then do is, since these observations is just scalars, it can use any univariate robust mean estimator here to come up with a bunch of clean observations. And then using these clean observations, it can run a least squares estimator and again get an estimate of the robust model theta hat. And for the mean of each arm A, it can then project this theta hat L onto the action to get a robust estimate of the mean of this arm A. Yes, this is again a legitimate strategy, but unfortunately, this too leads to a suboptimal regret bound. And this time, although we have been able to save on computation, this scheme requires a lot of communication because you're asking the agents to send up all their raw observations during the epoch. And the lengths of these epochs are expanding over time. So then this requires sending up a lot of information. So the main lessons that we learn here are, if we just naively try to use ideas from robust statistics, we might end up with loose regret bounds. We might incur a lot of computation and also a lot of communication. So the question is, can we fix these issues? And the answer is yes. And the main guiding observation here is that in the end, what do we really care about? We want to think about the projections of the latent parameter onto the actions, because those are the mean rewards. And in each of the strategies that I've shown you, the server is trying to compute a high dimensional estimate of the model, which is perhaps unnecessary. And this is creating unnecessary errors. Okay, so based on this observation, here's our idea in terms of computing robust ARM estimates. Each agent is again going to send up its local models. And when we want to think about computing the robust estimate of the mean of an action A, all we do is take that action and project it onto the local models sent by each of the agents. This gives us m scalar numbers. And then what we do is just take the median of these numbers. That's it. And this is very easy to implement computationally because you're taking a median of a bunch of scalars. So this is very easy to implement. And whatever comes out of this subroutine, we're going to interpret that as the robust mean estimate of action A, of the mean of action A, namely theta star. But this just gives us a point estimate. We also need to gain some understanding about the confidence intervals around this estimate. And the key guiding observation here is the fact that if I take any good agent I and I project an action A onto the local model of this agent I, then what I end up with is a Gaussian random variable with mean exactly equal to the mean of action A. Okay, so by this projection over here is a Gaussian random variable centered exactly at the object that I care about. So in the end, what you're really doing is that you have a bunch of Gaussian random variables, only a few of them are outliers, and you're taking a median of these objects. So this has a lot of structure, and we can exploit this structure to prove that with high probability for each active action, the gap between our estimate of the mean of that action and the true mean is bounded above by this confidence threshold gamma L, where gamma L is an inflated confidence threshold. Why do I call it inflated? We wanted a precision of order epsilon L. What we have ended up with is something that's slightly larger. And the reason why it's larger is this alpha square root m term. Okay, so you can think of this inflation as some additional slack, some conservatism to account for the additional uncertainty injected by the attackers. So then I guess this is going to answer the question that you raised, Ankita. What we have seen so far is how the server is computing estimates of the means of the arms and how it's computing confidence intervals around it. But now we want to understand, how does this translate into decision making? How does the server use these pieces of information to prune the active arm sets? Okay, so the idea here is that we look at all the actions within the current active arm set. We'll look at the action that has the highest robust mean estimate, and then we'll only retain those actions from the current active arm set in the next epoch, whose means are not too far away from the mean of the action that appears to be the best at this point. And the precision that we're willing to tolerate over here is twice gamma L, where gamma L is precisely the same confidence threshold that I showed you in the previous slide. It's the inflated confidence threshold. Okay, so we're looking at the arm that appears to be the best, based on the means that we have computed, throwing away arms that are far away from this. And by far away, I'm thinking about this confidence threshold gamma L that we have computed. Does that answer your question, Ankit, in terms of how the actions are pruned?
Yes, thank you.
Good. Okay, so very briefly, why does this work? This works because of two simple claims. The first claim is that with high probability, we can prove that the best action never gets eliminated. It manages to make its way through into every active arm set. And the second claim is that if a suboptimal action does manage to make its way into the L+1th epoch, then the instantaneous regret that you would suffer by playing that action can't be too large. It's going to be order gamma L. And recall that gamma L contains epsilon L, and epsilon L decays exponentially in the number of epochs. Okay, so as time progresses, if suboptimal actions manage to make their way into the active arm set, and I mean the regret that you will get by playing them has to be really low. That's the key equation. And if you put these claims together, it's not too hard to prove our final regret bound that I've shown. Okay, let me also spend maybe a couple of minutes just talking about our lower bound analysis.
So, sorry,
yes.
a couple of questions, Aritra.
Yes,
So here, the adversarial agents, countering the adversarial agents, you're doing it in two ways or one way? I mean, is the taking the median taking care of removing those adversarial effects, or is it this computing these robust confidence intervals? How are you exactly eliminating?
It's all of these, because I mean, in the end, our end goal is this decision making. So we want to be careful about the fact that we don't throw away good actions and we don't retain bad actions. And to do that, we need to get good estimates about the statistics of these actions, right? We need to get good estimates about the means of these actions and confidence intervals around variances. So everything that we're doing before this is trying to provide the basic ingredients that you need to achieve this decision making. So the median is giving you these estimates, these point estimates, and given to the fact that the noise in our system is Gaussian, we exploit that in the fact that you can get these confidence intervals for Gaussian random variables when you pass them through a median. So all of this is building up towards the decision making, the main point here is that when we create these confidence intervals, we need to be careful, because if these confidence intervals are too aggressive, then we risk eliminating the best action too soon. If they're too loose, then we incur large regret because they're too conservative. So it's a combination of all of these factors that play into the decision-making scheme over there. This is our end goal, and everything else is sort of building up towards this end goal.
Okay. And the second question is, you mentioned about that instead of estimating the theta star, you can estimate the projections, right? But what if, let's say, just for the sake of argument, if theta star is low dimensional, in that case, would your earlier strategies also be equivalent to this new strategy, or?
Yeah, that's a good question. If they're low dimensional, then this additional regret bound of a factor of square root d, I guess it becomes less important. Then you might wonder, which one is better. Yeah, so if d is low dimensional, again, this is subjective. What do we call low dimensional and what do we call high dimensional? It's not clear which strategy would be better, but nonetheless, regardless of what d is, you do suffer this extra square root d regret with these earlier candidate strategies, which you don't with the strategy that I just suggested. So now depending upon what d is, that determines how loose the regret bound is. And there's also this aspect of the implementation of the algorithm that usually scales exponentially in the dimension d. So you can imagine that even if d is not too large, maybe like 10 or 20, that's still going to cause these schemes to be quite heavy in terms of the computation. You need to do this in every epoch. So then that also limits what you can do. And the question is, why would you want to do that when it suffices to take scalars and take the median of that, and that causes you no extra factor in the regret. You to suffer no extra bound in the regret. So even if d is low dimensional, I think there's still incentive to using this as opposed to the other schemes.
Okay.
Yeah, good questions. So in the interest of time, maybe let me skip the analysis for the lower bound. Let me just say that the idea here is to construct two different bandit instances, each comprising of two arms, such that the best arm in the first instance is the second best arm in the second instance, this part is standard. This shows up in every lower bounding proof for bandits. But what's new is constructing the attack signals so that each of these instances appear to be observationally equivalent to the server. Okay, and if they appear observationally equivalent, then if you achieve good regret, if you're achieving low regret on one instant, it's you're going to necessarily incur a certain amount of regret on the second instance. So that's sort of the basic idea. And I'm happy to chat about this more offline. So to quickly summarize the first part of the talk, we proposed a new algorithm that provides near optimal regret bounds. It's computationally efficient, and it turns out it also requires very low communication. It's just log-T communication. And there are a few extensions in the paper pertaining to nonlinear observation models and contextual bandits. Okay, so in the little time that I have left, let me very quickly at least talk about what the formulation is for the second part of the talk. Let me motivate this formulation and walk you through the main results, and then I'll conclude. So what's the motivation? The motivation again is the fact that communication is a key challenge in distributed learning settings. And as such, there's been a lot of recent work trying to understand the effects of communication constraints on the performance of optimization algorithms. And perhaps the simplest abstraction that you can think of here is one where you have a worker agent and a server separated by a channel. The server at each time step sends down a model, to the worker. The worker computes a gradient of the loss function at this model. But when it tries to send back this gradient to the server, it needs to do so over a b-bit channel. And so it encodes the gradient using b-bits, transmits it to the server, and then the server does gradient descent on this using this quantized gradient. And so a natural question that you might think about here is, how many bits do we need to achieve the same convergence rates as you would get if the channel had infinite capacity? And despite the relative simplicity of this setting, a precise answer to this question was lacking. It was only recently provided by work by Prathamesh Mayakar and Himanshu Tyagi at IISc, and also work by Baba Kasibi and Victor de Costina's group at Caltech. Okay, but the thing to note here is that this is a static problem. Again, there's no decision making. Now, on the other hand, if you think about control problems or decision-making problems subject to communication constraints, there's a very rich literature at the intersection of control and information theory. And perhaps the simplest setting here is to think about the problem of stabilizing an NTI system over a bit constraint channel. Okay, so the idea here is that there's a controller that sends down a control input to a plant. The plant has, let's say, full state feedback, so it can observe the state exactly. But when it tries to relay the state back to the controller, it needs to again do so over a b-bit channel. Okay, so it encodes the state, sends it over to the controller, and then the controller uses the encoded state to take actions. So the question that one asks here is, how many bits do we need to stabilize the NTI system? And a precise answer to this question was provided in this very beautiful paper by Shekhar Tatikunda and Sanjay Mitra. And there's a very there's a huge body of work that's then followed up on this paper. So the thing to note here is that while this is a control problem, it involves dynamics, there is no uncertainty because both the encoder and the decoder have precise knowledge of the model's end of the system. Okay, so then given this premise, the question that we ask ourselves is, what's the simplest setup that we can think of that involves control, uncertainty, and communication constraints? Okay, so this is the setup that we ended up studying. What we have here is again a server and an agent separated by a channel, and at each time step, what the server is doing is that it's picking an action 80. In this case, we'll allow the action set to be more general than before. It's a time varying action set, and the agent then executes that action in the environment, and what it gets as feedback is a reward based on the same linear bandit model that I had shown you earlier. Now, the agent uses these observations to compute an estimate of the latent parameter, but when it tries to again send back this estimate of the parameter, it needs to do so over this b-bit channel. So this is again where the communication constraints play a role. So it sends back this quantized parameter, the server decodes the parameter and decides upon next actions. And the goal is exactly like before, to minimize the cumulative regret. So inspired by the Aritra Mitra formulation, what we have effectively done here is that we have separated sensing and control via this channel. And what's known here is the fact that if the channel capacity is infinite, then the optimal regret that we can hope to achieve in this case is O tilde d square root t, where d is the dimension of the latent parameter and t is the time horizon. So the question that we wanted to understand is, can we continue to achieve the same regret bound with a finite channel capacity b? And if so, under what conditions? And the reason why this is interesting is that you can imagine that for the server to take good decisions, it needs to gain understanding of this world. But all the information about this world is going through this channel. But the channel is distorting information, so it's distorting the view of the world as seen by the server. And this is going to take its toll on the decision-making process. And we need to ensure that these encoding errors don't compile over time. They don't build up over time. So in this case, our main contribution is to come up with a new algorithm, which we call the information-constrained linear CB algorithm. And the main result that we prove here is that as long as the capacity of the channel scales linearly with the dimension of the model, we can preserve exactly the same regret as you would get if the channel had infinite capacity. So beyond this sort of threshold rate, there is no loss in performance at all. And the main thing to note here is that this threshold bit capacity does not depend on the horizon t. If it did depend on the horizon t, then this would not be a nice result because the horizon t can be arbitrarily large. So the capacity would then be really large. And this sort of complements results of a similar flavor for stochastic optimization. This work by Mayekar and Tyagi. What they showed is that for preserving the optimal 1 over square root t rate for SGD, you necessarily need a capacity of d bits. Okay, so in our case, we don't have a lower bound on the rate, but at least we have an upper bound which suggests that perhaps d bits is what you need. The next question that we asked ourselves is, if the action sets happen to have more structure, can we hope to achieve optimal regret bounds with fewer bits? And to answer this, we considered the simpler multi-arm bandit problem. And and in this case, the actions is just the d orthonormal unit vectors. What we showed is that in this case, using just a 1-bit channel, you can achieve the optimal regret. So if you have more structure, then perhaps there's hope of doing better. And this result is pointing in that direction. I think I'm almost out of time. So let me just stop here by saying that I've talked about 2 different challenges, communication constraints and adversarial attacks in the context of sequential decision making. But there are a bunch of other themes that I'm interested in. In particular, one area that I'm quite excited about in understanding more is how do we sort of transfer policies across similar environments to achieve some kind of collaboration benefits. And we have some very preliminary work on this topic in the context of policy valuation. So in terms of future directions, there's really a lot to be explored in terms of different themes, robustness, information constraints, heterogeneity, and you can pretty much span the entire spectrum of decision-making problems. Right now, we're over here, we're really scratching the surface with the simplest class of RL problems, but there's a long way to go. So I'll stop here by saying that if you like these themes, then I'm looking for PhD students to work with me on these problems. So do consider applying to our PhD program. So thank you, and I'll be happy to take questions.
Thank you so much, Professor. So we can take 1 or 2 questions now.
Yeah, thanks, Aritra, for a very nice presentation. A couple of questions in this second problem. So here, you're not considering the dynamical system setting that was considered.
No. Yeah.
Okay.
Yeah. So that is a harder problem. I mean, because you need to think about stability. here, even without that, this turned out to be a bit complicated because this in the end relies on some kind of adaptive quantization scheme where we encode the innovations in this parameter theta, but those innovation signals end up being like random objects. So you need to be careful about how you're designing the range of your quantizer. In the Adversarial Mitra paper, those ranges are deterministic because there's no randomness. Here, because of the fact that there's uncertainty, there's noise here, the dynamic quantizer ranges themselves become random objects, and so that makes the analysis a bit harder, even for the static setting. But even if you made this a scalar over here and A was unknown, I think it would be interesting to think about what would be the analog of this problem when A is unknown. How do you design the quantizer ranges? What do you do? Would the capacity be the same in this paper as in this paper, or a bit more? So those are open questions.
Okay. And in the first talk, your strategy was to prune the action set as time progresses, right?
Yes.
But
yes.
And then you have a deterministic strategy. Once you have the action set, you deterministically do a round robin from those strategy. But one could also look at a stochastic strategy where you sample the actions in some probabilistic fashions, and you the probabilities you can take them down, right? So for some actions which are not, you think they could not be feasible, you can reduce the probability of those actions. So I'm just trying to think whether that stochastic strategy turns out to be equivalent to this, or maybe better or worse. Just a random thought.
That's a good question.
So basically, you're not eliminating it completely. You are still doing some exploration. You are keeping some scope for exploration still at every point in time, basically.
That's true. I don't know. I haven't thought about this point. That's a good point. That's a good question. The other thing that you could also do stochastically is, as time progresses, maybe you have a better understanding of which agents could be adversarial and which agents could not. And hence you might choose to weigh the information that you're getting from these different people based on some distribution, where over time you put more weight on the people that you think are more likely to be good agents, and you downgrade the weight on the adversarial agents. I think that could be done if you assume a bit more structure on the adversarial model. So perhaps, if the rewards are contaminated based on some biasing attack, then perhaps you can relate this to some kind of a detection scheme, attack detection scheme, where for each agent you maintain like a hypothesis, whether it's adversarial or not, and over time you adjust your beliefs on these hypotheses and use that to determine how much importance you want to put to the different agents. I think that could be an interesting scheme. In terms of the stochastic action scheme, while it might work, and it's definitely interesting, I'm not sure in terms of like what could be the benefits in the bounds, because I guess like the bound that we have now is, other than the fact that whether the square root d should be multiplying alpha, the bound is nearly tight in everything else. So I'm not sure whether you can hope to improve upon anything, but it might just be a very interesting conceptual. It might just be conceptually interesting to try out these other schemes. So, but I haven't thought about them.
Okay, thanks.
Professor, sir, I'm having a very small doubt. So you have formulated this using the Gaussian noise, right? So
yes.
Have you checked with any other noises? Does this regret bounds work with any other noises than Gaussian?
Yeah, that's a great question. So Gaussianity gives you a lot of structure. In particular, because the Gaussian distribution is symmetric about its mean, and the mean and the median coincide, that sort of informs the choice of the robust estimator, where you have this median operator. But the same analysis will also go through for sub-Gaussian distributions, and the regret that you will get, the dependence, the only thing that will really change here is, let's see. Yeah, so you have an alpha here, If with
Yes.
sub-Gaussian distributions, you'll get like a alpha square root log 1 over alpha kind of a term. So you'll have like a additional log factor dependence on the alpha. And what will change will also be the choice of the estimator here, the median estimator. There are other estimators that work well with sub-Gaussian distributions. So you can use any one of them. And actually in the paper, we do have a discussion of that point that, if the distribution is not Gaussian, if it's sub-Gaussian, then what do you do? If it's not even sub-Gaussian, but just bounded variance and IID, then things become a bit harder, because if your distribution is heavy-tailed, for instance, and you have adversarial agents, then it's harder to tell when you see something that's a bit different from the mean, whether it's because the distribution itself is heavy-tailed or because it's an outlier, because it's an adversarial. That's interesting, and there are estimators for heavy-tailed mean estimation. So like median of mean kind of estimators, trimmed mean kind of estimators. So it might be that you use one of them and it still works. But beyond the sub-Gaussian assumption, I haven't really worked it out and seen what happens. I presume that if you use any of these heavy-tailed mean estimators, then most of these ideas should hopefully carry through. But that's a good question.
Yeah. So thank you so much once again, Professor Aritra Mitra, so for a very interesting and engaging talk. So thank you everyone, and have a great evening.
Thank you so much. Thank you for the invitation. It's a pleasure.